de la UTEM desde 2019, ofreciendo cursos principales y electivos para programas de pregrado y posgrado en la Universidad de Atacama, actuando como integrante del comité de posgrado de la Universidad de Atacama desde diciembre de 2021. Su área de investigación se compone de nanomateriales funcionales para el cosechamiento de energía y remediación ambiental. Su diversa área de investigación basada en grafeno, generadores y detectores de nanopotencia, celdas combustible, nanomateriales para aplicaciones ópticas no lineares, tratamiento de agua contaminadas y membranas de filtración. Tiene muchos proyectos de FONDEF, Corfo, Fondesit, y ahora mismo es investigador principal de Fondesit Iniciación, que tiene fecha como de 2022 hasta 2025. Y hasta el momento ha publicado 48 artículos internacionales en WOS, un libro, 2 capítulos, y ha asistido a más de 10 conferencias internacionales. Así, más de 10 años de ascenso continuo como investigador y académico con ciertas habilidades. Así que nos va a presentar hoy el doctor Uray, el seminario que tiene como título Fundamentos y Aplicaciones de Nanoabsorbente. Bienvenido, doctor Uray, y te damos la palabra para que puedas hacer la presentación de tu seminario. Yo creo que está mutado. No sé si los otros lo escuchan. ¿Por qué está hablando?
No lo escuchamos.
No lo escuchamos. Sí.
Doctor Uray, no lo escuchamos.
Vamos,
no sé si puede ver tu micrófono.
Y ahora se escuchó bien.
Por ahora no sé.
Sí.
Y parece que está hablando. En el video se ve que está hablando.
Déjame ver. Mensaje directo mejor. Ah, sí está mutado. Sí, está mutado.
No. Ahora está activado. ¿Aló? Pero no se lo escucha.
Sí, tiene que ponerle volumen. Me parece que tenemos a Rada. A ver, me voy a comunicar con Rada para que...
Sí, Joe, I will call him in
¿Ya?
1 second.
Ahora sí. Ya.
Sí, lo que pasa es que el Rada... Volumen.
Sí. Yeah, I will call him.
Ya, ok.
వాయిస్ రావట్లేదు అది రావట్లేదు అది జాయిన్ విత్ కంప్యూటర్ ఆడియో పెట్టినా మరి ఒకసారి లాగౌట్ చేసి మరి లాగిన్ అవుతావా ఈ లోపు వీళ్ళకి ఇన్ఫార్మ్ చేస్తా he will be joining back one more time.
Okay.
Initially it is good, it seems. Inicialmente está bien, pero ahora...
Va a reiniciar de nuevo, ya. Okay.
Sí.
de algún programa, cuando tengamos estos impasse, le vamos a decir, mientras se arregla, vamos a mostrar un video del programa.
Buena idea.
¿No es cierto?
Sí.
Sí.
El angelito de Canal 13.
Bueno, para los que están llegando, lo que pasa es que el profesor tenía un problema con la parte, no lo escuchamos, así que se está, ahí ingresó nuevamente.
Ahora
Eso.
bien, ahora volvemos.
Ahora bien.
Sí.
The sound is good and clarity.
Sí, ok.
Yeah, we are.
Ready.
Yeah, you can begin this.
Yeah, okay. Let me allow some. Yeah, can you hear me good now? Everything is good? The video and presentation?
Yeah, we are. Yeah, we
Yes.
are hearing good. Yeah.
Yeah,
You can
first
begin.
of all, thank you for Abdullah and Catherine and others. And another thing is like, feliz cumpleaños Radha Manohar. Hoy es cumpleaños de Radha Manohar.
Happy birthday.
Feliz ahora. Yeah, okay. We will start with the presentation today. Basically, I prepared for the thing. It's a basic things about the adsorption and its application related to nano-absorbents. Probably, if the permit, in the next future presentations, I may present something more advanced related to research and investigation related things. But this is like a basic material, like related to the course, to the undergraduates, not to the level of the investigation or something. Okay. In this presentation, I would like to consider to cover some of the basics about the adsorption, the basic differences between the absorption and adsorption, the types what we have in adsorption, and how can we differentiate between two different processes, adsorption like absorption and chemisorption, and some details about the different isotherms, and about nano-absorbents like activated carbon, a general methodology to prepare activated carbon and its application. And finally, I give some inputs regarding the characterization of that nano-absorbent with bed. Except all the characterizations, I would like to focus on bed, because in case of nano-absorbents and absorption, the porosity, surface nature is much important. So I will focus with the bed also. The basic difference between absorption and adsorption is like there are two different phenomena. For example, if you consider the absorption, in absorption it is like a not completely surface phenomena. It involves the volume and it involves the energy levels and it involves some changes in the materials also. Whereas in adsorption, it is a temporary phenomenon, mostly related with the surface activity and a little bit with the porosity nature and volume level activity. Like the adsorption in gases are like liquid molecules onto surface of any solid surface or those. And when we consider the absorption and adsorption, the basic distinction is like absorption is not a spontaneous one, whereas adsorption is a spontaneous. Usually it takes place within a fraction of seconds on solid surfaces, for example, activated carbons. Very high molecular interactions are interactions between the active species present in absorption, whereas adsorption, less are negligible interactions. And involvement of potential or activation potential are how other energies involved in absorption. Whereas in case of adsorption, there is no much need of external parameters. Most probably it will with the systems like pressure, volume, and temperature. These are the critical factors when deciding the activity of adsorption also. So we can't divide the adsorption into categories, but adsorption can be divided into two types, basically like absorption and chemisorption. I just want to play some video here. Please let me know if you are not listening the sound. I will skip this video and I will go with the presentation.
Absorption and adsorption.
Can you hear the sound of the video?
Yes, we can hear.
Yeah.
Some tea accidentally falls while you're studying. What is the best way to remove it off immediately? Click on the right option. Yes. Now watch the tissue paper suck away the spilled liquid quickly. If we had used ordinary paper, the tea would not be completely absorbed. Tissue paper absorbs a liquid and ordinary paper adsorbs a liquid. How are these two different? Let us learn more on them. Let's understand absorption and adsorption a little better. Absorption is the passage of one substance into or through the bulk of another medium. The absorbed substance spreads to saturate the whole of the medium to form a solution. The mixing with the other medium's environment is so well that one fails to recognize its existence as a separate entity. In contrast, what happens during adsorption? Adsorption is the addition or sticking together of molecules of a gas, liquid, or dissolved solids to the surface of a solid or sometimes a liquid. The molecules are loosely held by the surface and can easily drop off. Let's see the difference between these processes. Absorption is seen in common day examples. Perfume spray is absorbed by our skin. Crisp finger chips turn soggy because they have absorbed moisture from the air. One substance is well soaked into a different medium. What about adsorption? Here is a jar containing a red dye dissolved in water. Look, what happens when a solid pellet of carbon is dropped into the jar? Well, isn't that surprising? The red color has almost disappeared in the jar. Why? The charcoal pellet has minute pores on its surface that cause the colored particles stick to it. The red dye undergoes the process of adsorption. Shake or warm this jar and lo, you get back the red color. Adsorption can be easily reversed by simple heating and is transitory. When a substance is absorbed in a different medium, it's called absorption. Usually, absorption cannot be reversed by simple means, although it may also be temporary. Now let's focus on adsorption by carbon and some practical applications. We could use adsorption for such diverse things like in deodorizing air in a refrigerator, decolorizing sugar solution, and controlling excessive acidity. Activated charcoal in a gas mask attracts toxic gas molecules, allowing the person wearing the mask to breathe fresh air. Drag the carbon pellet to each of the units displayed here, one by one, and observe the reactions that take place.
And I hope you got the idea of the difference between the absorption and adsorption. These two are two different phenomena. So let us focus on to the adsorption specific to the solid surface. Like the medium is like a solid medium, treating any gas molecules or gas medium or like liquid solutions. Let us go some details about the adsorption. As I said earlier, this is a surface phenomena, most probably for treating any liquid medium or maybe gas medium, the phase like gaseous phase or maybe liquid phase. There may be a peculiar interaction with the solid surface and the treatment medium, like maybe gas or liquid. The reverse of this adsorption, like if you can say in other words, one is like condensation, the other one is like evaporation. Condensation of gas molecules onto a surface like adsorption, and the reverse of adsorption is like evaporation of the molecules from the surface, that is desorption. So in this case, in adsorption, the molecules, they may can attach to the surface by two different mechanisms, like maybe physisorption or chemisorption. Say for example, if you go to the experimental side, if you go to the investigation level, say for example, if you have a solution like copper ions presented in a solution, and you want to treat that solution with activated carbon, the important factors that we need to consider while studying this theme, like treating copper ion solution with activated carbon. The most important factors are like quantity of the activated carbon we are using and concentration of the solution which contains the ions or which we only need to treat, and the active areas and the concentration of the dissolved copper ions. These are all comes into play to determine the experimental variables, such a way we can get the information related to the loading amount of the activated carbon and the limit of the adsorption of that activated carbon for that particular process. The main terminology that we use in adsorption is like the solid surface, what we call it as adsorbent, and the molecules, which one we are treating is like adsorbate, and the process is adsorption. Okay. By the end of this class, we will get how to get the experimental data and how to interpret these things and how to get the information related to the adsorption process one by one here. So absorption is a technical term that represents both the processes. It's a combination of absorption and adsorption. Both the process, the combination what we call in general is a absorption. So normally when we consider the adsorption, there are different causes, there are different mechanisms which affect, which is the driving force in adsorption process. For example, what we know, the contact angle with the water molecule with any surface that defines the hydrophilic nature or hydrophobic nature. The two different things is hydrophilic and the one is hydrophobic. If it is repelling the water, not allowing the wetting the surfaces, what we call it as like a hydrophobicity. So when we consider the adsorbent and adsorbates, the attractions or the mechanism in the adsorption depends upon three different types of attractions or three different types of force. One is like weak attraction, that is physical attraction, van der Waals force related attraction. The other one is electrostatic, which present when we are treating with the ionic molecules or ionic surfaces. The last one is like chemical forces, temporary bonding formations, maybe either hydrogen bonding or maybe pi bonding, which are temporarily in nature. The weak attraction, it might be between the two different molecules, or electrostatic attraction between the different charges, or maybe formation of hydrogen bond and another bonds that are weak in nature, are the causes for adsorption process in systems. So as I said earlier, exchange adsorption, physical absorption, and chemical absorption, three different types. In exchange, it relates to the presence of ions. And physical attraction, it's a weak in nature and is easily reversible, and it doesn't relate on to the most of the surface properties. It's capable of multi-layer formations also. The chemical adsorption, as its name indicates, it involves some bonding formations. So it may be a little bit stronger when compared to the other two. And it is highly specific in surface morphology and also for the typical monolayer formations. So generally the combination will present in normal samples in real time. If you are working with activated carbon or another nanostructures, the combination of physical and chemical will exist there and dominates them most of the adsorption. If you say in absorption, considering the solid surface as the medium, the adsorbent and adsorbates, there are specific terminologies and definitions we need to understand before understanding the total absorption mechanism. The most important thing is like the surface coverage area, usually denoted with theta. This is like the permutations and combination probability of occupying the available vacant sites by the gas molecule or maybe the liquid molecule. So it is a ratio which defines the probability between the available sites and the occupied sites. So obviously it's a ratio, it will be the value from 0 to 1. And usually in absorption process, the temperature is also very important factor in determining the things. So either it may be exothermic or endothermic by liberating heat or by taking heat energy. Before going the isotherms, Langmuir isotherm and wet isotherm, we need to little bit understand about the rate kinetics or rate laws with respect to the concentrations and time. The rate law for any chemical reaction that relates with the concentration or maybe time or maybe the partial pressure of the reactants will be defined in different isotherms, and there are three definite laws, that is zero, first order and second order. I just try to give the brief idea about and how they can be related with our nano-adsorbent and adsorption process and to the wet. Say for example, consider any generic chemical reaction between two reactants. Say for example, capital A and capital B are the reactants, and the small letters indicates the stoichiometric compositions and resulting in a formation of a product C. This is a representation with no intermediates in the formation of a product. Okay, in this case, generally the rate of formation of this product will be expressed with this expression. Here the K is what we call it as the rate constant, and the upper brackets A and B represent the concentration of the reactant species in moles per liter is a general unit to be there. And the exponents, usually they called it like order, that represents the order of the reaction that proceedings there, and sum of this order is called total sum of the reaction order. And this K is much important in considering the reaction rate laws, and that represent the rate constant. This rate constant signifies irrespective of the concentrations, like initial concentrations of the reactants. The rate constant represents the how far, how effective, how the rate, the speed of the reaction. And also we can consider the influence, and we can study the influence of temperature, pressure and surface area, etc. for that particular reaction while monitoring this rate constant value. Say for example, if you see considering the different rate laws, before going to the rate laws, consider these things. If there is only involvement of one reactant that result into products, this is unimolecular. If there are two similar, that is bimolecular, or two different also bimolecular. The corresponding rate constant will vary according to your number of reactants involved in that reaction. Normally, as I said earlier, the rate constant indicates how effective is the reaction. So the smaller the value of the K indicates that reaction is slow. If it is larger, it indicates a faster reaction. So it defines the how rapid is the reaction in the formation of the product. So when we go to this thing, the are something, the integers, we call it as like reaction orders, and these are not related to stoichiometric equations. These are like expressing the order of the reaction with respect to the formation of products, and these can be calculated and determined experimentally only. And this experimentally only, we need some specific experimental trial and error methods to determine the values of these things. And some of these things, what we call it as overall reaction order. Say for example, this is an example of reaction with nitric oxide with oxygen and formation of nitrous oxide. We can represent this one with a rate law. Here the exponent 2 indicates this reaction is second order in nitric oxide and first order in oxygen. Overall, this is a third order reaction. A similar example here also. As I said earlier, there are three types of rate laws: zero, first and second order. And within these three laws, there are two different types of representations. One is differential form and the other one is integrated form. So the differential form, if you see the differential form, it actually depends on the concentration. The variation of the concentration with respect to time is the differential form. Whereas in the case of the integrated, it gives the how the variation of this concentration with respect to time also. Now let us see some zero order reaction. What is meant by zero order reaction is actually there is no definite dependency on the total concentration of the reactant. It means the rate constant is a constant itself and it is not a function of the concentration of the reactant. So for example, this is the decomposition mechanism of hydrogen iodide on gold catalyst, which is a peculiar zero order reaction, which indicates K into concentration of hydrogen iodide with power 0. This 0 indicates the zero order reaction. Obviously, the rate of the decomposition of this reaction is directly proportional to the rate constant, which means it is independent on the concentration. So this is the general case. If we go to the rate law in general, so the rate law in differential form indicates the variation of the concentration. So this is the rate for a reaction of reactant A. And the negative sign indicates the decomposition because the reactants reacted together to form the product. So obviously this indicates the depletion of the concentration of the reactants. So this is a general form for a first order reaction. And if you go to the general order, like rate constant of a zero order reaction, as I said earlier, without concentration, only the rate constant, that is the zeroth order. So applying some integrations and proper limits, like integrating the proper limits from 0 to time t and the corresponding initial concentration to final concentration at t, what we get is the mathematical representation for integrated law of zeroth order. This is like similar to y equals to mx plus c. So if you plot the values of the concentration with respect to time, what we get is a straight line or with a negative slope. So this represents here the concentration with reaction rate. As I said, this is a constant. So obviously the reaction rate is constant and it is not a function of concentration. This is a zero order reaction. Whereas in case of zero order reaction itself, the slope will give the value of the rate constant once we know the value of the concentration variation with respect to time. The another important factor in this thing is half time, which is the time required to deplete to the half of the initial concentration. So considering that thing, considering the half of the initial concentration here, the time at half of the initial concentration T off, and this value gives the time dependence needed for the half of the reactants to get reduced or to get converted into the resultant products. One of the famous example for this zero order reaction is reverse of Haber process, the production of ammonia. And as I said earlier, the method of initial rates. So the orders, what we express as the exponents for the concentrations, should be calculated from experimental determinations. So the method of initial rates is the method used for the determining the orders of the reactions. And let us see the first order reaction here. In first order reaction itself, it's a function of the concentration. So method of initial rates to determine the reaction order comes experimentally. So for example, consider an experimental setup or reaction here. And if you express the rate with respect to nitric pentoxide, this rate will be considered with a power m. This is the order of the reaction with considering this reactant. So this dependence on the concentration and the rate of this reaction obviously directly related with the concentration of the reactant, and also we can calculate the order of the reaction with respect to this reactant using initial experimentals. Say for example, we have varied the initial concentration of this reactant from 2 to 3 variants. Say for example, with 2 variants, rate 1 signifies one reaction with initial concentration of N2A and another initial concentration to N. So considering these two, And if you know the rate of these reactions, we can calculate the value of the order using the equation of the rate. And once you got the value of the order, we can calculate the value of the rate constant by using any one of the experimental equations. And the corresponding integrated law for first order we can express by considering the integration on both sides, applying the proper limits for time is like 0 from initials to final time t, the corresponding concentrations A0 and AT. What we get is like a exponential decay of the concentration in case of first order reactions. So the reactants will be exponentially decay with respect to time in case of first order reactions. So if you rewrite this equation and if you considering the log, applying the log normal on both sides, we can modify this thing to much simpler form so that we can have a good interpretation from the graphical representation. So considering this equation as y equals to mx plus c, it should be like a straight line, and the slope gives the value of the rate constant k, and the intercept will give the initial concentration from that reactions. So in such a way, by doing some initial experiments, we can calculate the rate constant of the reaction, and also we can observe the values of the rate of the reactions. Likewise, as I said earlier, the half-life also indicates the time required to deplete to the half of the initial reactant concentration. In case of first order reactions, it is as we know that rate constant is a constant in overall, this half-life is constant in case of first order reaction. What it indicates, for every half-life of time, the products will be doubled or maybe increased. The reactants will be depleted to the half of its initial values. In second order reactions, it's a little bit complicated when compared with the zeroth order and first order, because in second order, as we say, the second order we can consider in two types. One is like either it may be second order in one of the reactants. Say consider this general equation involving of two reactants and formation of one product. So if it is a second order, either it may be second order in any one of the reactants, maybe with A or maybe with B, or maybe it's a combination of two first orders. The first order in A and first order in B, the overall reaction is like second order with respect to both the first order reactions. Either way, it is a second order equation. So in case of second order equation, if you apply the differential form and integrated rate law, what we get is like the relation between these two. In case of if you consider the two first orders like A and B with different initial reactants, for example, if it is both the reactants are same, it may be converted to the same like second order in one of the reactants. So if they are initially different reactants, so obviously the equation will be different. If you consider the same integrated form here, the parameters, experimental parameters may be little bit different. What we are varying is the initial concentrations and the time we are considering. So if you plot the values of 1 by 80, that means with respect to time, so we will get a straight line. The corresponding slope will give the values here. The most probably here is the difference between the choosing the parameters to obtain the linear plot. If you see in zero order, we choose directly the concentration with respect to time, which gives a linear plot so that we can get the values of the rate constant. Whereas in case of first order, we need to choose the log value of a concentration with respect to time. That gives the linear plot to obtain the parameters of the concentration. Whereas in second order, reciprocals we consider with respect to time. So we will get the rate constant. Obviously, the rate constants, with the rate constants and the initial set of experiments, we can get the order of the reactions. These order of the reactions and rate constants are much important when considering the lag-Muir isotherms and beta isotherms. This one is like representing the order of the reactions in like reactions. So this just represent the overall idea about the zero order, first order and second order. So in zero order, directly the rate constant is a independent of concentration, whereas in first order, the rate constant will be directly proportional and it's a linear. In case of the second order, it's a gradient. For a particular like that one. I will give some example here so that we can get a little bit idea about the method of initial rates to obtain the order of the reactions. Say for example, we have a chemical reaction like this and performed 3 different experiments by varying the concentration of the initial reactants. This one is the initial concentration for ClO2 and initial concentration for OH. So we have 3 different experiments and we have the corresponding initial rates. So we have the rate values. What we need is order with respect to ClO2, like exponent values. So consider any of these two. First, write the rate equation. So rate equation is K multiplied by concentration of ClO2 with exponent M and concentration of OH with respect to exponent N. This 1 and 2 represents different experiments, experiment 1 and experiment 2. So considering these 2 experiments and substituting the corresponding values as we know from the data, so we can get the value of M, and in this case the value of M is like 2. The 2 indicates here the reaction here is second order with respect to ClO2. Likewise, we can get the value of the order N, that means order with respect to OH, by considering the another set of experiments here. So we choose the parameters in such a way to simplify the equations so we can get the value of M. So now we have the orders like order with respect to ClO2 and order with respect to OH. So the overall order is 2 with 1, it's like 3. So finally we can express the rate law. So the rate is equal to K, like rate constant, with concentration of ClO2 with the order of 2 and with concentration of OH in the order of 1. Okay, this is the rate equation we have. So once we have the rate equation, we can get the value of the rate constant also, because we know the values of the rates here, initial rates, the formation of products. So by considering any one of the experimental, either experiment 1 or maybe 2 or maybe 3, any one, we can get the value of K. By choosing any one of these experiments, as it is a constant, we will get the same value. So considering the first experiment and substituting the corresponding values from the experiment 1, we can get the value, or considering the experiment 2 also, we can get the same value. Finally, we have the value for the rate constant and the corresponding units. So this is a constant value. Whatever the experiment here, if you use the parameters properly, the value will be same. And this is like a similar example. So I skip this thing. And now let us do some other different set of experiments. Earlier we have the rate values. So probably it is not easy to get the rate values directly from the experiments. So what we can do is experimentally, we can vary the concentration, or we can note the concentration with respect to time. So experimentally we have the values like time and the variation of concentration of the one of the reactant NO2 with respect to time. We have only this experimental data. From this, we can get the order with respect to NO2. Also, we can get the rate law. Also, we can get the quantity or concentration left after a particular time also. So considering this equation here, this is like applying experimental data to the graphical mode, and from the graphs we can obtain the information. It's like backward process. So considering the integrated laws, these are the 3 integrated laws like 0, first order and second order. So we know the value of T and we know the concentrations with respect to T, which indicates the 0 means initial time 0, the corresponding is initial concentration A0, and corresponding values are AT. So we can plot the corresponding plots between the time with respect to either maybe direct concentration or maybe log value or maybe reciprocal of the concentration, correspondingly related to the each order. This is for 0 order reaction, considering the reaction as 0 order, or considering it as a first order, or considering it as a second order. So once we have the plots, what we can do is we can fit the data, and this is a linear equation, so we can fit the data, we can get the slope value and intercepts. The fit, the goodness of the fit of the data will give the idea which one is the better representation. Say for example, this R square is the goodness of the fit from the experimental data. If you see the best value obtained in, if you consider the second order. So obviously the reaction is in second order with respect to NO2. So finally, we can have the values from the fitted data, like y equals mx plus c. So we can get the slope value and with the intercept. The intercept is the initial one, 2.01. And obviously, once we have the rate equation here, and t is the time variant. So obviously, we have a optimized plot. From that, we can get the calibrated plot. We can get the value of the concentration left over after a particular time. So if we substitute the corresponding time, we can get the value of the concentration of the NO2 after a particular time. This is another way to deal with the experimental data in rate kinetics. So let us come to the absorption. So in absorption, obviously there is an equilibrium between the adsorbed molecules and dissolved molecules. So for example, consider a granular activated carbon particle or activated carbon. If it is a porous, this crack represents a porosity in that molecule or porosity in that substance. So the boundary, most interesting part is the boundary of that particles, boundary of the nanoparticles or activated carbon particles. And cracks are porous nature in this. What will happen is slowly the molecules start to occupy the surface and also start to fill the vacuum space here, like porous nature here. So once it is start filling, at a stage, it will be in equilibrium, means the number of particles occupying the surface will be in equilibrium with the number of particles leaving from the surface. Adsorption and desorption, the rate of adsorption and rate of desorption will be equal. That is the equilibrium condition. Means number of incoming and number of outgoing will be in a constant phase. This equilibrium condition is very important theoretically to deduce the mathematical expressions and to understand the mechanism related to adsorption. While considering the adsorption, Langmuir adsorption isotherm is the first one to represent mathematically and to identify some parameters that involved in the adsorption process. Langmuir as a scientist considered some assumptions considering the system like solid phase and liquid phase, or maybe solid phase with gas phase. When we considering the solid phase, that is adsorbent. In adsorbents, we can have two types of structures, either may be homogeneous or may be heterogeneous with respect to its surface nature. So homogeneous indicates the equal number of pores and with equal dimensions. Okay, the surface roughness will be same. Whereas heterogeneous, there may be higher pores, there may be smaller ones, there may be bigger, or there may be onto the surface or much deeper into the volume also. So in considering the liquid phase, absorption, desorption, both mechanisms will be there, and there may be an equilibrium there, and either may be exothermal in case of adsorption and endothermal in case of desorption. So the partitioning between gas phase and absorbed spaces as a function of applied pressure. This is the basic idea in obtaining the isotherms, applied pressures. Say for example, consider we have a tank with a surface like maybe activated carbon enclosed with a gas phase. the gas phase continuously in movement. Some of the gas molecules come and rest on the surface of the solid surface, and some may be dissolved. At a particular time, the adsorption and desorption will be at equal rate. That is the equilibrium condition. So considering the gas A, molecules A and solid surfaces B, and the resultant as AB, the rate of adsorption and rate of desorption will be the same when there is a dynamic equilibrium existed. So considering the equilibrium conditions and considering the following assumptions, Langmuir proposed isotherm to understand the adsorption in solid liquid phase or solid gaseous phase. In considering the Langmuir, these are the basic assumptions, means the number of vacants or absorption sites on the particular surface. Like for example, considering the homogeneous, the surface should be homogeneous and the number of vacant sites are fixed. And all these have the equal probability to get attached with a gas molecule or maybe liquid molecule. And the absorption is only monolayer or unilayer. I will try to give the explanation what is meant by monolayer and multilayer in the next PB, in next slides. You will get understand what is the basic difference between the monolayer assumption and multilayer assumption also. Okay. Also, the most important assumption in Langmuir is there are no interactions between the gaseous molecules or liquid molecules like adsorbents, and also no interaction with the surface also. And dynamic equilibrium will always exist there. Once one of the molecule get captured at the surface, it is immobile, means it cannot move from this place to another place. Only the option is it can be dissolved and it can get settled in another position. Okay, adsorption followed by the desorption. There is no alternative movement between the molecules that absorb on the surface. So considering the equilibrium, as I said, equilibrium, dynamic equilibrium means rate of adsorption and rate of desorption will be same. So considering these things, if you consider rate of adsorption as rate constant Ka and rate of desorption as Kt, means rate of forward reaction and rate of reverse reaction. Forward means adsorption and the reverse is desorption. So in case of forward, it's a combination of concentration of the solid surface and concentration of the active species. And rate of reverse is like a combination of the both. So obviously at equilibrium, what will happen? These two will be same. Rate of forward reaction is equal to rate of backward reaction. By rearranging the things, the ratio of these things, the adsorption and desorption, usually represented with a constant K, the overall rate constant, is a function of the concentration of the final and initial reactants. For this to understand, I explained the rate constants. Okay, the rate laws, the same thing here, rate of forward reactions and rate of backward reactions, which is a function of the concentration of the reactants and products. Okay, based on this equilibrium condition, what we have is a relation between the concentrations of the surfactant or solid phase and gaseous phases with rate constant. So considering this relation, this is, and considering the assumptions and considering the pressure, let us go a little bit detailed about the absorption in a solid surface by gas molecules, considering the Langmuir assumptions. For example, see, consider this is the surface of aluminum. Each block represents a vacant sites. Okay, we have an aluminum surface that is going to absorb nitrogen gas. So considering the alumina surface, each block has vacant sites that are capable of capturing one of the gas molecules, like for example, nitrogen. Okay, say for example, if a nitrogen molecule occupied at completed site, this one is vacant. After some time, if you increase the pressure, as we are dealing with the solid and gas system, pressure is the driving force. So if you increase the pressure, more number of gas molecules get occupied to the surface. So it's going to fill the vacant sites. Once they're completely filled, it is a monolayer. Monolayer representing the formation of a film or a layer of gas molecules that occupy the overall surface of the solid phase by one molecule itself, not like a capped ones. It's a single molecule that forming a filmy nature on the surface. So considering this, and theta is the occupancy, the probability of the occupying the sites. Here the theta represents the number of sites of the surface which are covered with gaseous molecule. Say for example, in this case, 3 out of like 7. 3 by 7 is the theta value, occupied sites. It gives a ratio with respect to the total, as I said earlier, number of occupied sites to the number of total available sites. So 1 minus theta will give the total number of vacant sites. Considering these two, now we can write the rate of forward reaction and rate of adsorption. Okay, or rate of desorption or rate of backward reaction. As I said, forward reaction means adsorption. Adsorption is derived by the pressure applied. So obviously it proportional to pressure and it proportional to the total number of vacant sites. Because for absorption to occur, there should be some vacant sites. So the total probability of vacant sites, 1 minus theta and pressure are related with the rate of adsorption. Okay. Considering and introducing the constant Ka, the rate constant for adsorption, we have the relation for the rate of adsorption. Ka with pressure and 1 minus theta is the number of vacant sites. If it is desorption, rate of desorption is proportional to the already occupied sites, means the theta. If it is already occupied, then only it can be dissolved. Then only it can release the molecule so that then other adsorption will come. So the rate of desorption directly proportional to theta, and it is not a function of any other parameter. Okay. In this rate of desorption, considering these two and considering the fact of dynamic equilibrium, these two will be equal, the rate of adsorption and rate of desorption. For that, what we have directly, we can get the relation between the occupancy, pressure and rate constant. As we have already introduced a parameter that K equals to ratio of adsorption and desorptions. So we have the final value between the occupancy theta with pressure and rate constant. This is the isothermal representation for mathematical representation for the Langmuir isotherm. And we can choose another alternative form for this Langmuir adsorption by considering the solid gas system. So if you consider the solid gas systems, considering the values of the volume of the total gas absorbed and volume of the monolayer, that is volume required to form a one single molecule occupied and that cover the total surface. So this is the volume required to cover the total surface, that will be by V mono, that is volume of the monolayer and volume of the total gas absorbed under given sets of conditions like pressure, volume and temperature, dealing with the ideal gas system, dealing with the gaseous system. So this is the ratio which gives the occupancy in terms of volume. Considering this factor and substituting these values, we have a final relation between the pressure, volume of the monolayer, and this will be useful as experimental conditions to obtain the values related to the volume of the monolayer and porosity natures. But accordingly, there are some limitations to the Langmuir. They behave ideally in vapor phase, and adsorption monolayer, it is a limitation, and surface should be homogeneous, it is also a limitation. Weak forces of attraction also, it is a limitation, and liquefaction also limitations. So to overcome this, another proposed the BET. BET is a multi-layer adsorption, and I skipped all the introductions. I will go to the details. So considering the same methodology, and finally what we have is a expression for the BET. If I have the time, I can continue or I can skip.
You can 5 minutes more or less.
Yeah, okay.
Yeah.
I will skip the BET and I will go to the activated carbon so that I will.
Okay, man.
In case of activated carbon, let us come to the activated carbon class. Here, what we have is activated carbon with porosity nature is the major driving force in adsorption. Usually, activated carbon can be obtained from different sources that available nature, like nutshells, any of the nutshells, avocado, olive, grapes, all the nutshells, and coconut husk, wood, coal. By using some physical activation or maybe chemical activation, we can convert the existing charcoal to activated carbon. There is a big difference between the existing charcoal and activated carbon. So we can use some physical activations by treating with the high temperature or low temperature or some technical pressure volume variations. It will give physical activation. Or by treating with some other chemicals like reactants, acid treatments, we can activate the charcoal into activated carbon. So what will happen is actually considering the raw material, this activated carbon is low in organic content and ease of activation, also availability of the raw materials, low cost in preparation, and low degradation upon storage, and very less impact on the environmental factor also. So when we consider the activated carbon, the energy required with respect to the theme of industrialization for the applying to the industrial scale, we need to consider the factors like the energy input, material input, water input to obtain the nano-adsorbent like activated carbon, and its use and its end life as absorbent, and ultimately the environmental impact. These will comes into play when we are applying the non-absorbent in industrial scales. Normally, the activated carbons have amorphous nature or maybe porosity within the different ranges like nanometers to micrometers. Based on this absorption and based on the characteristics, they based on its availability, like maybe powder form or maybe granulated form or maybe pellets. The future depends upon its porosity, level of activity, and level of purity. Obviously, the different applications will depend upon its different characteristics. So nowadays, the activated carbon is applied in many applications like food industry, and treatment of water, pharmaceutical waste treatment, all other these things. If you consider the relevant nanomaterials like carbon nanotubes, polymeric substances, zeolites, nanosilver, titanium dioxide, titania, magnetic nanoparticles, some other well-known nanoabsorbents. Obviously, these nanoabsorbents, based on its porous nature, either may be obtained from its agglomerated form, or maybe its peculiar formation of the structures, or maybe the targeted porosity nature that obtained from the chemical treatment. And the size of the porous nature will define its effectiveness in removing the pollutants or treating the contaminated waters. So if you see the analysis of these samples with respect to bed will give the idea of this is the same formula that obtained in bed theory, which is a function of the pressure and relative pressure P naught and the size distributions here. We can get the value of the pore size and also we can get the surface area by analyzing the bed theories. So in bed theory, basically, there is a study related to its relative pressure, P by P naught, with respect to the specific amount of the gas absorbed, that is nitrogen in general they use to study this thing. And the type of the isotherm will give the idea of the type of the activity of the adsorption process. Either maybe it's monolayer or maybe multi-layer or maybe volume adsorption. And these graphs will give the values of the surface area, total surface area available, total active surface area, and volume of the monolayer and volume of the total gas absorbed with respect to the considering the pressure, volume, and temperature. We can get the pore diameter or pore radius that of the molecule. This is the basic things that related with the activated carbon, and the application will definitely depending upon its porosity and also with its nature and also with its preparation. So by this, I will close the class here. I'm sorry, I cannot conclude all the things within the time period, but maybe next time I can give a clear idea about the activated carbons or other things that to the investigations level. Thank you.
Thank you very much, Uday, for the presentation.
Yeah.
And I think we can begin with the question. I don't know if anyone have a question, because in the chat we have
thank you, Uday, for the detailed presentation. So I have one query regarding this. So whether this adsorption occurs on charged absorbents or absorbents, whether the pH of the nano absorbents and absorbents influence during the absorption
Yeah,
kinetics?
it influence. Actually, what will happen is the adsorption has a definite influence on some particular parameter. I skipped the slide, but I will show you the thing. If you consider the adsorption as extent, there are some definite parameters that affect these things, like solubility of the system and pH of the system, temperature of the system, process. These are all influencing factors that affect the adsorption process.
Okay, fine. And one more thing, sometimes.
No, sometimes if in experimental studies, like investigation studies, people used to do one of the studies based on varying one of these parameters, like varying the temperature and studying the capacity of adsorption of the nanocarbon, varying the pH, varying the particular conditions. We can study the whole set of nature of these samples.
Yeah. Yes. And one more thing, I have one more doubt regarding energy storage applications. As you know, some of the materials shows like excellent specific capacitance, even though there is less surface area. So whether this kinetics plays the role?
Yes, it plays the role. Because in nano absorbents, the basic phenomenon is adsorption. More the active surface area, more the activity. See, for example, if you have the less smaller size particles with more access to the surface, the more access to the surface indicates more porous in nature. If you consider volume porosity, if you have canal-like nature, channels, so we have more access to the overall available surface. This overall availability will obviously improve the performance of the material. Means more storage of the active components, more storage of the reaction species on the surface.
Yes. Yeah. Anyway, thank you so much for the clarification of the doubts and the detailed presentation.
Yeah. Thank you.
I don't know if there are another question for Uday. Well, Uday, I have one question because I work with water remediation, and using this process, sometimes we have some issue because after absorption, we need to, because in this process, there are only a transfer of contaminant to the medium contaminant to the absorbent. And after the process, I think there are a need to remove the contaminant from the absorbent.
Yeah.
One kind of process you use.
Yeah.
Yeah.
It is like the end life of nano-absorbent. In this case, what we need to study is that what I said. I just covered the basics of these things. If you consider the investigation part, there comes these things. How to use and capacity, the percentage of the quantity, what we need to load, like loading amount of the activities. After that, we need to study the recycling and reproduction of the material what we use, regeneration of the material. Once we use it for absorbing some material, we need to propose some desorption mechanism also. Later, we need to study the recycle and reusability of that material. That comes to the part of investigation, like the R&D section. So I didn't cover this part, but this comes when we consider the overall picture. That's what I put at this diagram. By considering the overall industrial scale, we need to consider the production cost, overall production cost, and overall operation cost, and overall maintenance cost, which means reproduction and regeneration of the absorbents what we use. Like every catalyst is industries what they use. Recover of catalyst or recover of the main active component and reusability of that component. When considering the other materials, the raw materials for activated carbon very cheap. Like for example, the bio waste like nutshells, any organic materials like as I said here. These are all sources of the activated carbon which are very cheap or less in cost. So obviously the production cost will be less. For industrial adoption, it will be much easier when comparing with the other type of absorbent.
Okay, yeah. Okay, thank you very much for the explanation. And I don't know, there are another question. Yeah, thank you very much, Uday. Very clear presentation and very educative. And we will close, I think, the seminar for now. and thank you for the participation in this seminar. And see you in another time.
Yeah, see you.
Y muchas gracias todo por la presentación. Yo creo que cerramos. No sé si Catherine tiene algo que decir.
No, déjame ver si hay no, nadie más. Muchas gracias por el seminario UDEI y bueno,
Gracias.
están
Muchas
abiertos
gracias a
para
todos.
colaboraciones.
Thank you.
Muchas gracias a todos por su asistencia. Hasta mañana.
Ok, chao.
Chao.
Chao, gracias a todos. Chao.
Gracias a todos, hasta luego.
Thank you, Dai.
Thank you.
Muchas gracias por la presentación.
Gracias. Sí.